Chapter 17, Example 3, and what we have here is a circuit that performs one of two things depending on the quality of the input. So what we have here, it's either outputting a -1 or it's outputting A plus B. So those are our main clues there. So let's go ahead and draw our top level black box diagram first. There's my starting point in this. Top level black box diagram, this is it. Next thing I want to do is take an inventory of the internal modules that I'll need to do this. First of all, I see it's adding A plus B. I only have one way of adding things, and that's with a ripple carry adder. The circuit is outputting one of two things. It's either outputting the sum or it's outputting a -1. So it's making a choice. The choice that it's making is what to output, of course, and that means for our circuit it absolutely needs a mux. So I'm going to go ahead and draw a mux in there and do the final connection here. Do some other connections. So next thing I want to do is try to connect the interior parts of this circuit. The first thing, many places to start here, is to see what the output is going to choose between. So it's going to choose between A plus B, which is the sum, and also it's going to choose between -1. So these are all 8-bit values. And so this is a shorthand notation for 1 1 1 1 1 1 1 1. Now it's like the only negative number I know, and signed format is all ones is -1. So this gives me the -1, this input gives me the -1, this input's the sum. So the issue here is what's controlling this mux. The mux has a control input. In particular, what are we going to connect it to? So we read back on the problem, and it says if both inputs are both negative or both positive, it outputs -1. So the way I know whether an input is negative or positive is to look at the sign bit. The issue is this calls out a classic if both negative, if both positive, according to the sign bits. That calls out for a gate, and so that's going to be an equivalence gate, which we know as an XNOR gate. So that means it's worth drawing. Let's draw it real fast. 1 0 0 1. Okay, so this is my gate, and what it's saying is when both inputs are positive or both inputs are negative, it indicates this on this output. So this is what is going to control the mux, and the inputs to this gate are going to be the sign bits coming off the input operands, which I need to mark here. I have to do one more thing here. Essentially, I need to put numbers on these things to disambiguate this. So I just took a guess. I have to go back and check to see if the guess is right. So if these are both 1 or both 0, this is going to be 1. This signal is going to be a 1. It needs to select this one up here. Okay, so once again, I guessed wrong, and I'm going to go back and change it. This is actually should be 1 and 0. So I'll check that again. If both these inputs are 1 or both a 0, this is a 1, and it chooses a 1 to be passed to the output. So this number, these 1s are hard-coded here. Interesting thing about this problem is, do I ever have to worry that this answer is valid, or if this sum is valid? And the answer is no, because the two invalid cases are associated when the sign bits of the two input operands are the same. Where in this particular circuit we have a special case for that. If they're the same, it selects the -1 anyway, which means if they're different, this value is always going to be valid, because anytime I add two numbers of different sign, the magnitude is going to shrink. Therefore, it's always going to be in a valid range. So the answer is always going to be valid. So a little clever little problem, has some kind of intricacies in it that you should be aware of. So lastly, the issue is what controls this circuit. That means what is connecting to the control input of this mux. Remember, there's a choice being made according to that control input, and what we have connected to that is an internal signal. So this is an internally controlled, and with that, we'll just put a box around it.